April 8th, 1941. Nakajima's test airfield, just outside Tokyo. The afternoon sun hangs low, a pale light glinting off polished fuselages. A massive aircraft rests on the runway, its wings stretching nearly 140 feet, casting a shadow over the tarmac. For engines rumble, a low, throaty growl that vibrates through the soles of the engineers' boots. Sweat beads on foreheads despite the spring warmth. Inside the cockpit, the pilot's hands tighten around the throttles. He can feel the aircraft's weight beneath him, a behemoth built from stolen blueprints and borrowed dreams. This is no ordinary plane. It is the product of ambition, espionage, and hope. Japan's first four-engine land bomber. On the ground, engineers stand rigid, eyes locked on every detail. The flex of the wings, the strain of the landing gear, the hesitant hum of the engines. Every instrument reading is scrutinized, every movement cataloged. This aircraft carries not just fuel and metal, but the promise of reaching across oceans, of striking at distant targets. And yet, there is unease. The engines shudder against the weight. Controls feel sluggish. The aircraft lifts slowly, almost reluctantly, into the humid Japanese air. For a brief moment, time seems to pause. History is being written, but not in the way anyone expects. This is the story of dreams, of imitation, and of ambition meeting limits. It is a story that begins not with triumph, but with tension. The year was 1935. America was on the cusp of an aviation revolution. Airlines were expanding, air travel was shedding its novelty, and manufacturers were locked in fierce competition to design the next generation of aircraft. Douglas Aircraft Company had just unveiled the DC-3, an airliner that would soon become legendary. But even before the DC-3 had fully proven itself, visionaries in the airline industry were dreaming bigger. William Patterson, president of United Airlines, had an audacious idea. An airliner capable of crossing the continent without stopping for fuel, carrying dozens of passengers in comfort, with pressurized cabins and air conditioning. It was a concept almost beyond reach in 1935. Douglas engineers understood the ambition and the risk. Building a four-engine airliner, one that could combine size, range, and reliability, would push the boundaries of contemporary aviation technology. Patterson was not alone. American Airlines, Eastern Airlines, Pan American Airways, and Transcontinental and Western Air all expressed interest. Together, they funded a $500,000 development program to realize the vision. Arthur Raymond, who had led the DC-3 program, took charge of the new project. The challenges were immense, designing wings strong enough to carry four engines, creating landing gear capable of supporting a 60,000-pound aircraft, and routing systems for fuel, hydraulics, and electricity through a pressurized, passenger-ready fuselage. By 1938, after more than 8,000 engineering drawings, hundreds of wind tunnel tests, and over 1.3 million rivets, the prototype DC-4 emerged. The aircraft was revolutionary. Its tricycle landing gear allowed level ground handling. Its massive wings promised lift and stability, and its distinctive triple tail reduced overall height while maintaining control. Inside, the cabin offered a new level of luxury: sleeper berths, wide seating, and climate control. On June 7, 1938, the DC-4 lifted off the Santa Monica runway for the first time under the control of test pilot Carl Cover, a man who had flown the DC-1, DC-2, and DC-3 before it. The aircraft handled well, but the complexity of its systems hinted at challenges to come. Despite its technical brilliance, the DC-4 proved difficult for daily airline operations. Its fuel consumption was high, maintenance demanding, and performance fell short once passenger loads increased. By 1939, airlines were withdrawing from the program, leaving Douglas with a sophisticated but commercially unviable aircraft. It was a failure in the eyes of its American creators, but its story was far from over. Across the Pacific, Japan's military and industrial leaders were watching closely. The Imperial Japanese Navy recognized the strategic potential of a long-range, four-engine aircraft. Japan had achieved remarkable success with nimble fighters like the Zero and twin-engine bombers, such as the G-4 Mbedi, but had no experience building heavy, four-engine land bombers. The distances of the Pacific demanded range and payload that twin-engine designs could not provide. The DC-4, though rejected by its native country, offered a shortcut. Here was a ready-made, advanced airframe that could serve as a template for Japan's own strategic ambitions. In late 1939, representatives from Japan's Mitsui Trading Company approached Douglas with a purchase proposal. Officially, the buyer was Japan Airlines, the Nippon Koku, a rapidly expanding commercial carrier. The offered price of $950,000 was substantial, and for Douglas, it represented a way to recoup some losses from a program that had consumed millions in development costs. The transaction appeared routine, a foreign airline buying an American aircraft for civilian use. Export controls on commercial aircraft were minimal, and no one suspected the deeper intentions hidden behind the transaction. Douglas disassembled the prototype and shipped it to Japan, complete with technical files, engineering drawings, and wind tunnel models. Japanese engineers watched the reassembly carefully at Haneda Airport. To the Americans, this was normal customer support. To the Japanese, it was a masterclass in reverse engineering. The aircraft would serve as the blueprint for what would become the Nakajima G5N, Japan's first attempt at a strategic four-engine land bomber. The DC-4's arrival in Japan marked a turning point, not for American commercial aviation, but for the ambitions of a nation preparing for war. It was a purchase steeped in deception, with the apparent civilian transfer masking the Navy's true objectives. The stage was set for an experiment that would test the limits of imitation, engineering, and ambition. And yet, for all its promise, the DC-4 carried within it the seeds of failure. Its weight, complexity, and temperamental systems, problems that had made it impractical for American airlines, would become Japan's burden to bear. The story of the G5N was about to begin, and it would be a tale of ambition colliding with reality. Context/background, Section 2. By early 1940, the DC-4 prototype had arrived at Nakajima's test facility under the guise of a commercial airliner. Publicly, it was a new Japan Airlines flagship. Privately, it was a blueprint for Japan's first strategic bomber. Japanese engineers dismantled every component with meticulous care, measuring, photographing, and documenting each part. Every rivet, every control cable, every hydraulic line became a data point in an immense reverse engineering project. Nakajima's goal was clear: replicate the DC-4's advanced design while converting it into a heavy bomber capable of carrying a full payload over the vast expanse of the Pacific. Where the DC-4 had carried passengers, the G5N would carry bombs and torpedoes. The cabin became a bomb bay. The nose was reshaped for a bombardier station. Defensive gun positions were added in the nose, waist, dorsal, and tail. The triple tail of the DC-4 was replaced by a twin fin arrangement, simpler to manufacture, yet functional for control. Power was a major concern. The original DC-4 used 4 Pratt & Whitney R-21 80 Twin Hornet engines, each producing 1,450 horsepower. Nakajima decided to fit their own NK-7A Memori engines, each rated at 1,870 horsepower, reasoning that greater power would offset the additional weight of military equipment. The aircraft now measured over 100 feet in length with a wingspan approaching 140 feet, dwarfing all previous Japanese designs. The tricycle landing gear, copied directly from the DC-4, gave the G5N better ground handling than any other Japanese bomber. The first prototype, designated G5N1 and nicknamed Shinsen, Deep Mountain, was completed in early 1941. On April 8th, at 2:35 p.m., it rolled down Nakajima's runway for its maiden flight. Imperial Japanese Navy observers watched as the massive aircraft lifted into the humid sky. Onlookers were awed by its size and modernity. Yet within minutes, the flaws became apparent. The G5N was heavy, even beyond expectations. The Memori engines failed to deliver reliable power, often overheating and vibrating during sustained climbs. Flight controls felt sluggish, unresponsive compared to the lighter twin-engine aircraft Japanese pilots were accustomed to. Climb rates were slow. Maximum speed peaked at only 261 miles per hour, slower than contemporary American and British heavy bombers. Range fell short of the Navy's 3,000 nautical mile requirement, limiting operational reach across the Pacific. Nakajima attempted to correct these deficiencies. Subsequent prototypes incorporated tweaks to engine cowlings, propeller pitches, and fuel systems. Later, two G5 and 2 variants replaced the Memori engines with Mitsubishi 4 billion Malawian Kwacha's Kase engines, known for reliability but producing only 1,530 horsepower, significantly less than required. The result was a bomber even slower and less capable than the original. Weight, complexity, and engine limitations formed a vicious cycle that could not be broken. Despite these setbacks, the Navy persisted for a time, hoping incremental improvements might salvage the project. The Army considered using the design for its own purposes, proposing variants Ki-68 and Ki-85. Full-scale mock-ups were built, but by 1943, the Army abandoned the program, recognizing the fundamental flaws. Nakajima's G5N remained the Navy's responsibility, but the bomber's combat future was bleak. Eventually, the Navy repurposed 4 surviving G5N prototypes as long-range transports. The offensive and defensive armament was reduced or removed entirely. Crew numbers dropped from 10 to 6, and the aircraft served in supply roles for the remainder of the war, flying to Hong Kong, Formosa, Tinian, and the Philippines. The Shinsen became a transport, a shadow of its original ambition, its potential as a strategic weapon unrealized. The irony was profound. The DC-4, rejected by American Airlines for being too complex, had been sold to Japan under the guise of civilian aviation. The Japanese Navy, seeking to convert it into a bomber, inherited all of its flaws and added new ones through misapplied modifications. Ambition collided with engineering reality, producing a machine admired for size and modernity, but incapable of fulfilling its intended mission. American intelligence later identified the G5N through aerial reconnaissance and assigned it the code name Liz, believing it to be a strategic bomber threat. In reality, the aircraft had been relegated to cargo transport years before the Allies understood its true condition. The story of the G5N underscores a critical lesson. Technology cannot simply be copied. The physical design is only part of the picture. The experience, knowledge, and problem-solving that produced it are equally vital. Nakajima had the DC-4 in crates, but they lacked the institutional insight to avoid the missteps that had hampered its development. Douglas, having learned from its DC-4 failures, would later create the C-54 Skymaster, one of the most successful 4-engine transports in history. Japan, in contrast, produced a cautionary tale of overreach, a massive bomber that could not bomb, a dream grounded by weight, power, and ambition. The G5N Shinsen's troubled development naturally leads us to examine the story from multiple perspectives: the human, tactical, technological, and leadership angles that shaped its creation and ultimate failure. The story of the G5N Shinsen is as much about people as it is about metal and engines. At Nakajima, engineers worked tirelessly to dissect the DC-4. Their days were long, measured not in hours but in rivets, blueprints, and torque wrenches. For these men, the aircraft represented both ambition and national pride, a chance to leapfrog decades of Western aviation progress in a single program. Yet for pilots, the G5N was an enigma. Flight crews accustomed to nimble fighters like the Zero or twin-engine bombers like the G4M Betty suddenly faced a lumbering giant. Test flights revealed a machine that did not respond intuitively, that resisted commands and demanded constant adjustment. Many pilots later described the experience as fighting against the aircraft rather than with it. The physical strain was compounded by mental stress. A heavy bomber with unreliable engines was not just inefficient, it was dangerous. Pilots carried the anxiety of knowing that any climb, any maneuver, could be compromised by overheating engines or sluggish controls. Beyond Nakajima, the human story extended to Allied observers. Intelligence analysts in Australia and the United States, studying photographs of the G5N, faced the challenge of assessing a new threat from afar. They saw a massive aircraft that could theoretically project power across the Pacific. They imagined the possibilities of a Japanese strategic bomber reaching Hawaii or even the American mainland. Their concern was real, yet it was based on incomplete information. The G5N, they did not know, would never fulfill that threat. Human ambition, fear, and pride intersected at every stage of the G5N's life. The aircraft was a monument to Japanese wartime determination, a testament to the lengths a nation would go to gain technological parity. But it also highlighted the limits of individual skill and human ingenuity when facing fundamental engineering constraints. Tactical perspective. From a tactical standpoint, the G5N was an ambitious but flawed attempt to solve a strategic problem: how to strike across the Pacific. Japan's early successes with carrier aviation and twin-engine bombers had provided operational reach, but not the kind required for intercontinental strike missions. A four-engine land-based bomber promised range, payload, and flexibility. In theory, the Shinsen could have changed the tactical landscape. Its bomb bay could carry 8,800 pounds of ordnance or 2 aerial torpedoes. Its size and tricycle landing gear offered stability for long missions. If it had worked, it might have allowed Japan to strike distant Allied bases with a payload comparable to contemporary American bombers. Naval planners imagined raids on Hawaii or the Aleutians, long-range reconnaissance missions, and even logistical resupply of remote garrisons. Reality, however, diverged sharply from theory. The G5N's sluggish climb rate and limited speed made it vulnerable to interception. Its range fell short of operational requirements, leaving it incapable of reaching many key targets. Engineers tried to optimize engine performance and reduce weight, but every modification highlighted another limitation. In tactical exercises, the Shinsen could not sustain the altitude or speed necessary to evade enemy fighters or anti-aircraft fire. By the time the Navy accepted its limitations and repurposed the aircraft as a transport, the tactical role had shifted entirely. The bomber that might have projected offensive power across the Pacific became a logistical tool, ferrying cargo and personnel to Japanese outposts. Even then, it retained value only because its range allowed it to serve distant islands inaccessible to smaller aircraft. Tactically, the G5N story illustrates a crucial point. Technological ambition alone cannot guarantee battlefield effectiveness. Even a machine modeled on an advanced American design falters if its engines, weight, and handling characteristics fail to match operational requirements. Planners, engineers, and pilots all learned that a theoretical advantage is meaningless without practical performance. The human and tactical perspectives are intertwined. Engineers wrestled with technical limitations, pilots struggled with operational realities, and commanders adjusted expectations in response. The stage was set for deeper exploration of technological and leadership angles, where the interplay between design ambition and strategic intent would further illuminate the rise and fall of the Shinsen. Technological perspective. The G5N Shinsen was, at its core, a cautionary tale of technological imitation without understanding. Nakajima engineers had before them one of the most advanced American commercial airliners ever built, the DC-4 prototype, but they lacked the context that had guided its development. Every rivet, every control surface, every engine cowling could be measured and copied, yet the design's subtleties, the lessons embedded in years of testing, failure, and refinement, remained invisible. One of the central technological challenges was weight. The DC-4 had already grown heavier than projected in American service, a problem exacerbated by the addition of military hardware in the G5N. Nakajima's engineers attempted to compensate with the Memori engines, rated at 1,870 horsepower, Yet even at full power, the aircraft struggled to lift off smoothly. Heat, vibration, and mechanical unreliability plagued every flight. Replacing the Memori with the proven but lower-powered Mitsubishi 4 billion Malawian Kwacha's engines solved reliability but worsened performance. The Shinsen became a paradox, safer to fly, but incapable of performing its intended mission. Aerodynamics and control presented another technological hurdle. The G5N retained the DC-4's wing configuration and tricycle landing gear, innovations that had transformed American air travel. But its fuselage had been elongated, its bomb bays enlarged, and its defensive armaments added. The result was a machine that looked imposing, yet was fundamentally misbalanced. Flight controls were sluggish, handling was poor, and climb performance lagged far behind contemporary heavy bombers. The story of the G5N underscores a profound lesson. Technology is more than a collection of parts. It is knowledge, experience, and judgment combined. The Japanese had acquired the parts. They did not acquire the understanding. Without grasping why Douglas engineers had made certain compromises, they repeated mistakes while introducing new ones. The Shinsen was an artifact of both aspiration and miscalculation, a striking example of how advanced designs can fail without the wisdom to apply them effectively. Leadership perspective. The leadership behind the Shinsen program faced a delicate balancing act between ambition, secrecy, and operational need. At the highest levels, Imperial Japanese Navy planners were driven by a strategic imperative. Japan needed long-range bombers capable of striking the American Pacific. They believed that the DC-4 offered a shortcut, a technological bridge to the capabilities they lacked. Naval leaders sanctioned its acquisition, financing, and secret transfer through Japan Airlines, demonstrating boldness and cunning in strategy and subterfuge. At Nakajima, leadership confronted a different challenge: how to turn a civilian prototype into a credible military asset. Engineers and test pilots needed direction, resources, and oversight. Leaders had to prioritize engine development, structural analysis, and crew training, all while managing timelines and secrecy. Their choices, selecting the Memori engine, modifying the fuselage, and attempting multiple prototypes, reflected both ambition and limited understanding. Each decision carried consequences, often compounding the aircraft's inherent flaws. Leadership failure, however, was subtle. There were no glaring mistakes in judgment, only misaligned assumptions. Planners assumed that a copied airframe could be transformed into a strategic bomber with sufficient engine power. They overestimated the capability of Japanese industry to produce reliable 14-cylinder radial engines and underestimated the impact of added weight from military equipment. Their vision was strategically sound, but technically infeasible. The consequences of these decisions extended beyond the Shinsen itself. Resources, manpower, and industrial capacity were tied to a program that could not deliver its intended results. Commanders had to make hard choices: persist with a flawed bomber, repurpose it, or cancel the project entirely. Ultimately, they chose pragmatism, converting the surviving aircraft into transports. This decision salvaged some operational value while acknowledging a fundamental failure of technological foresight. The leadership angle reinforces the human and tactical perspectives explored earlier. Ambition, vision, and strategic intent clashed with technological reality and operational limitations. The G5N Shinsen stands as a testament to the complex interplay between human will, industrial capability, and the immutable laws of physics. April 8, 1941. Nakajima's airfield outside Tokyo was unusually quiet for a spring afternoon. The sun filtered through high clouds, casting long shadows across the concrete runway. The prototype G5N Shinsen, a massive four-engine bomber, sat poised for its maiden flight. Its fuselage gleamed under the muted light, the nose glazed for the bombardier, dorsal and tail turrets bristling with guns. The pilots, veterans of Japan's burgeoning air force, approached with caution. They knew the aircraft's size and complexity, made it unlike anything they had flown before. The NK-7A Memori engines roared to life one by one, vibrations rippling through the airframe. Smoke spiraled from the exhaust stacks, an ominous reminder of the challenges ahead. At precisely 2:35 p.m., the pilot eased the throttles forward. The bomber lumbered down the runway, each wheel thudding against the tarmac. Slowly, almost reluctantly, it lifted into the humid spring air. Observers held their breath. The climb rate was sluggish. Controls were heavy, unresponsive. The Shinsen did not soar. It struggled, straining against its own weight. Minutes into the flight, the problems became evident. The Memori engines, theoretically rated at 1,870 horsepower each, failed to deliver consistent power. One engine faltered, sending shudders through the wing. The aircraft pitched slightly, the autopilot non-existent, and the crew fought to maintain stability. Temperatures spiked in the cowlings. Vibrations thrummed through the fuselage, forcing constant corrections. The test flight revealed a brutal truth. The Shinsen was overweight, underpowered, and poorly balanced for its intended mission. Each added turret, each reinforced bulkhead, each structural modification designed to adapt the DC-4 airframe to military needs had compounded its flaws. The engines could not compensate. The bomber that Japanese planners had hoped would dominate the Pacific sky struggled to remain airborne. Subsequent test flights offered no relief. Engineers attempted incremental improvements, adjusting propeller pitch, modifying engine cowls, and fine-tuning control surfaces. A second prototype performed slightly better but remained painfully inadequate. The climb rate barely improved. Speed was still lower than the minimum required for strategic operations. The airframe groaned under the added weight of bombs, fuel, and defensive armament. By mid-1941, the Shinsen had become a study in limitations. The ambitious vision of a long-range Japanese heavy bomber collided with industrial reality. The Memori engines overheated during climbs, reducing reliability. Swapping them for Mitsubishi 4 billion Malawian Kwacha's engines improved mechanical stability, but sacrificed even more performance. Now the bomber could fly safely, but it could not reach targets across the Pacific or evade enemy fighters. The realization hit the Imperial Japanese Navy with force. They had invested years, millions of yen, and national prestige into a bomber that could not fulfill its strategic purpose. The G5N was supposed to threaten Pearl Harbor or strike American holdings across the Pacific. Instead, it was a lumbering transport, vulnerable and slow. By 1942, the verdict was clear. Even with modifications and careful piloting, the Shinsen could not operate as a combat bomber. The pilots who flew it described it as overweight, sluggish, and unforgiving. Engineers documented its limitations meticulously, noting engine failures, structural strain, and poor handling characteristics. The aircraft's promise had unraveled in the air, irreversibly and definitively. Despite the mounting evidence, the program did not immediately end. Nakajima built additional prototypes, attempting to resolve the technical deficiencies. Each new iteration, G5N2 with Mitsubishi engines, minor structural modifications, adjustments to armament, failed to deliver the desired leap in capability. The aircraft was trapped in a vicious cycle. Stronger engines were unreliable, reliable engines were too weak, structural modifications added weight, and weight degraded performance. By the end of 1942, the G5N program reached its operational breaking point. Leadership faced an undeniable decision: continue attempting to salvage a strategic bomber that could not perform its mission, or repurpose it to extract any practical value. The decision was made to convert surviving aircraft into transports. Offensive armament was removed, bomb bays sealed, and crews reduced. 4 of the 6 prototypes were redescribed as G5N2L Shinsenkai, serving solely in cargo and personnel transport roles. Even in this reduced capacity, the aircraft's limitations remained visible. Pilots struggled with weight distribution, engine reliability, and long-distance planning. Every flight reminded observers that the Shinsen had never achieved its intended purpose. The climax of the Shinsen story is not a single moment of destruction, but a slow, relentless revelation. The aircraft that had been expected to dominate the skies was fundamentally incapable of fulfilling its strategic promise. From its first tentative takeoff to its repurposed cargo missions, the G5NS trajectory is defined by hope, ambition, and the inexorable reality of engineering limitations. By mid-1942, the Imperial Japanese Navy faced an uncomfortable truth. The G5 in Shinsen could never fulfill its intended role. Reports from the test pilots were grim. Even with engine detuning and incremental adjustments, the aircraft remained underpowered, sluggish, and operationally unreliable. Any attempt to deploy it as a long-range bomber would expose crews to near-certain danger from enemy fighters and anti-aircraft artillery. The consequences were immediate. Naval planners who had envisioned the Shinsen striking at distant American bases across the Pacific were forced to revise strategy. Operations that had assumed a fleet of four-engine heavy bombers now had to rely on twin-engine aircraft like the G4M Betty, which could fly long distances but carried significantly smaller payloads and offered no comparable defensive capability. The Navy's grand plan for strategic bombing over Hawaii or the continental United States quietly evaporated. Nakajima's engineers continued testing, desperate to salvage the program. Each prototype flight became a lesson in limitation. The G5N2 variant, equipped with Mitsubishi 4 billion Malawin Quachas engines, was more reliable than its Memori-powered predecessors, but sacrificed speed and altitude performance. The aircraft could now complete long-range transport missions, but at the cost of its original offensive ambition. Crews noted that climb rates were insufficient to evade enemy aircraft, and maximum speed was consistently below thresholds for effective combat operations. Internal documents from Nakajima reveal the depth of frustration. Engineers repeatedly noted that no existing Japanese engine could provide sufficient power for the G5NS airframe while maintaining reliability. Modifications to the wings, control surfaces, or weight distribution provided only marginal improvements. The aircraft had reached the limits of Japanese aeronautical engineering at the time. Despite these setbacks, the Navy did not immediately terminate the program. The Shinsen's sheer size and long-range potential made it useful as a transport. 4 of the 6 prototypes were converted into cargo aircraft, the G5N2L Shinsenkai. Bomb bays were sealed, armaments removed, and crews reduced to a minimum necessary to operate the plane. These transports flew supplies to distant garrisons across the Japanese Empire: Hong Kong, Formosa, Tinian, the Philippines, and the Mariana Islands. Even in this reduced role, the aircraft was a logistical asset, delivering engines, spare parts, and personnel where smaller aircraft could not reach. But the strategic ambitions that had driven the G5NS development were gone. The dream of a Japanese 4-engine bomber capable of threatening Pearl Harbor or the continental United States was irrevocably dead. By 1943, both Navy and Army planners recognized that no amount of engineering modification could transform the Shinsen into a combat-ready bomber. The Army had explored its own variants, the Ki-68 and Ki-85, but canceled both programs after seeing the Navy's struggles. The collapse of the Shinsen program was a costly lesson in overreach. Japan had purchased the DC-4E prototype from Douglas Aircraft, reverse-engineered it, and invested years of labor, material, and money. The project consumed resources, engineering hours, engine production, test pilots that could have been applied to more viable aircraft designs. Yet, instead of producing a formidable weapon, the Shinsen highlighted the limitations of imitation without understanding. Japan had copied the external form and systems of an advanced American aircraft, but lacked the institutional knowledge, engine reliability, and manufacturing depth to make it successful. Allied reconnaissance eventually identified the G5 in Japanese airfields, photographing the massive 4-engine aircraft. Analysts assigned the code name Liz, assuming it was a dangerous strategic bomber. In reality, the Allies overestimated the threat. By the time intelligence reports circulated, the aircraft had already been relegated to transport missions, far from the intended offensive role. The deception, whether intentional or accidental, demonstrated the disconnect between design intent and operational reality. The final flights of the Shinsen were utilitarian. Crews flew long-range supply missions over vast stretches of the Pacific, navigating typhoons, mechanical failures, and the ever-present threat of Allied interception. Despite its limitations, the aircraft's long-range capability allowed Japan to maintain tenuous supply lines to remote outposts, a small consolation for a program born of ambition but grounded in failure. By 1944, the Shinsen was obsolete, for surviving transport aircraft were worn from extended service. Spare parts were scarce, maintenance intensive, and the airframes had aged beyond practical use. None of the 6 original prototypes survived the war. Reports indicate that some were destroyed during Allied bombing raids. Others were scrapped for materials. The Shinsen's physical presence vanished, leaving only photographs, technical drawings, and the memories of engineers and pilots who had labored on the program. The climax of the G5N story lies not in a dramatic air battle, but in the relentless exposure of human ambition clashing with technological reality. Japan's hope for a strategic bomber capable of altering the course of the Pacific War ended not in combat, but in the hangars of Nakajima, machines grounded, engines overworked, dreams unfulfilled. The story of the Shinsen naturally leads to the aftermath, where we examine how its failure influenced Japanese strategy, resource allocation, and wartime decision-making. The failure of the G5 in Shinsen cast a long shadow over the Imperial Japanese Navy's aviation ambitions. What had begun as a bold plan to field Japan's first 4-engine heavy bomber ended in a humbling lesson about technological limits, overreach, and the perils of imitation. The Navy's high command, which had poured resources into the program since 1939, was forced to reconsider its strategy in the Pacific. Operationally, the loss of a viable strategic bomber left Japan reliant on twin-engine aircraft like the G4M Betty and the Ki-21 Sally for long-range missions. These aircraft, while capable of reaching distant targets, were vulnerable to interception, underarmed, and had limited payloads. The Shinsen had promised to deliver long-range bombing capability with defensive resilience and payload capacity, but in reality, it had delivered only weight, complexity, and disappointment. The industrial impact was significant. Nakajima had devoted thousands of man-hours, specialized machinery, and critical resources to building the prototypes. Engineers and technicians were assigned to painstaking reverse engineering, producing detailed drawings and diagrams from the DC-4E. That effort, while technically impressive, diverted manpower and materials away from other aircraft programs that could have yielded combat-ready machines. Aircraft like the A6M0, which became Japan's most iconic fighter, were still being produced, but the G5N program competed for engines, workshops, and skilled labor that could have accelerated other production lines. Financially, the Navy had invested heavily in the project. By the time the G5N program was scaled down to transport aircraft, millions of yen had been spent on development, prototypes, and test flights. In the context of wartime resource scarcity, this was a substantial cost, both in material and opportunity. The money and manpower expended on the Shinsen could have supported a fleet of proven medium bombers or additional fighters, equipment that might have had a tangible impact in the early years of the Pacific War. The Shinsen's failure also revealed weaknesses in Japanese project management and strategic foresight. Unlike Douglas Aircraft in the United States, which had decades of experience developing large multi-engine airliners, Nakajima and other Japanese manufacturers were attempting to leapfrog generations of technology. Without the institutional knowledge or systematic testing procedures that had guided the DC-4ES development, Nakajima engineers struggled to anticipate and resolve the compounded problems of weight, power, and reliability. The result was a machine that looked formidable on paper but could not perform its mission. Morale within the Navy's aviation branch suffered as well. Pilots assigned to the G5N program faced repeated frustrations in the air. Test flights confirmed that the aircraft was sluggish, underpowered, and dangerous at the operational limits required for a combat mission. Crews developed a quiet cynicism toward the bomber. Some observers noted that, even as a transport, the Shinsen required constant vigilance and meticulous handling to avoid accidents. The gap between expectation and reality became a source of embarrassment and a reminder that technological ambition must be matched by practical execution. Strategically, the Shinsen's shortcomings forced Japanese planners to adopt a more conservative approach. Long-range bombing of the American mainland remained a distant dream. Instead, Japan focused on consolidating gains in the Pacific, relying on naval power, carrier aviation, and existing twin-engine bombers to project force. The failure of the G5N demonstrated that Japan could not simply buy or copy foreign technology and expect instant operational success. Every innovation required careful integration, testing, and adaptation, a lesson that came too late to influence early war strategy. The narrative of the Shinsen also entered Japanese propaganda and public perception, but only superficially. Officially, the aircraft had vanished, a supposed crash in Tokyo Bay covering its true fate. The public never knew the extent of the program or its failure. Within the Navy, however, the lesson was clear: ambition without engineering foundation, imitation without understanding, and over-reliance on improving technology could be catastrophic. The stage was now set for the next phase of the story: how the G5N prototypes were repurposed as transports, their operational role reduced, and the long-term consequences of the program on Japan's wartime logistics, strategy, and engineering priorities. Aftermath, Section 2, From Bomber to Transport. The G5N's operational role. By 1942, the Imperial Japanese Navy had accepted a bitter reality. The G5N Shinsen would never fulfill its original role as a long-range strategic bomber. Yet, scrapping the aircraft entirely would waste resources already expended. Nakajima engineers and naval planners therefore embarked on a pragmatic solution, converting the surviving prototypes into long-range transport aircraft. The 4 aircraft that survived the G5N program were stripped of most armament. The dorsal and tail turrets, the ventral and nose guns, and heavy armor were removed to reduce weight. The bomb bays, designed for payloads of up to 4,000 kilograms, were either sealed or adapted for cargo storage. Crew complements were reduced from the original 7 to 10 men to a minimal 6-man flight crew. These modifications transformed the Shinsen from a failed bomber into a logistical asset, one capable of reaching distant Japanese bases in the Pacific with payloads of personnel, equipment, and essential supplies. The reconfigured aircraft were assigned to the 1021st Kokutai, a specialized naval transport unit operating from Kotoriai Air Base. This unit became the sole operator of the G5N transports. Their missions, though far removed from the grand vision of bombing Pearl Harbor or U.S. coastal targets, were nonetheless critical. The Pacific theater presented enormous logistical challenges. Many Japanese garrisons were scattered across islands hundreds of miles apart, often with limited sea supply lines threatened by Allied submarines. The Shinsen's range and payload, inherited from the DC-4ES transcontinental design, allowed the Japanese to maintain tenuous supply chains to remote bases such as Hong Kong, Formosa, Tinian, the Philippines, and the Mariana Islands. Despite this repurposing, the Shinsen remained a difficult aircraft to operate. Its weight and handling characteristics continued to challenge pilots. Engine reliability, while somewhat improved with the switch from the Mamori to the Mitsubishi 4 billion Malawian Quachas Kasei engines, remained marginal for long flights over open ocean. Maintenance crews required specialized training to keep these aircraft airworthy, limiting operational flexibility. The 1021st Kokutai, therefore, had only 4 functional aircraft at any given time, a tiny fraction of Japan's transport fleet. From an Allied perspective, the Shinsen remained a mysterious and intimidating presence. Aerial reconnaissance photos captured the massive four-engine aircraft on Japanese airfields, prompting intelligence analysts to assign it the code name Liz. Allied planners, unaware that Japan had abandoned its strategic bomber role, prepared contingency plans to counter a potential long-range threat. In reality, the aircraft posed no strategic bombing risk. It existed only as a transport, quietly moving cargo across the empire, its reputation as a bomber a ghost of unfulfilled ambition. The G5N's operational life underscores the broader lesson of Japan's wartime aviation strategy. Ambitious programs, particularly those involving technology beyond the current domestic industrial base, carried immense risks. Even when projects failed to deliver their intended combat capabilities, Japan attempted to extract residual value wherever possible. The Shinsen's conversion into a transport was an example of adaptability in the face of failure, yet it could not compensate for the opportunity cost of years of development and the diversion of critical resources from other, more viable aircraft programs. By 1944 to 1945, as Allied bombing intensified and Japanese industry faced severe shortages, the remaining G5N transports were pressed into increasingly desperate service. They carried munitions, spare parts, and sometimes medical evacuations. Their slow speed and size made them vulnerable, and by the final months of the war, none survived intact. Records of their exact fates are incomplete, but it is likely that Allied attacks, mechanical failures, and cannibalization for parts eliminated the fleet entirely. The story of the Shinsen, from its DC-4E origins to its final role as a cargo hauler, highlights a recurring theme in military technology. Advanced designs do not automatically translate into effective capability. Resources, industrial know-how, and operational context are as critical as the machines themselves. In Japan's case, the pursuit of a four-engine heavy bomber, a dream built on purchased and copied technology, ended in practical failure, but offered a cautionary example that influenced future aircraft programs. The transition from grand bomber to humble transport naturally leads to the next chapter, the reflection on lessons learned, not just for Japan, but for the broader history of aviation and the consequences of copying technology without understanding its foundations. Reflection/closure. Lessons in ambition, imitation, and innovation. The story of the DC-4E and the G5N Shinsen is a cautionary tale about ambition, imitation, and the limits of technology. On one side of the Pacific, American engineers at Douglas labored for years, navigating unknown challenges, testing, failing, and adapting. Their triumph was not just a machine. It was the accumulation of knowledge, experience, and institutional memory. When they eventually created the C-54 Sky, they transformed a failed airliner into one of the most reliable transport aircraft of the Second World War, powering supply lines across oceans and supporting both military and humanitarian missions. Across the Pacific, the Japanese experience with the G5N was the mirror opposite. Purchasing the DC-4E promised a shortcut to strategic air power. Yet even as Nakajima engineers meticulously copied every rivet, bolt, and wing panel, the aircraft's soul, the hard-earned lessons embedded in its design, remained inaccessible. The Shinsen inherited not only the structure of the DC-4E but also its flaws. Heavy, underpowered, and mechanically unreliable, it could never fulfill its intended purpose. The grand dream of striking across the Pacific dissolved, leaving only 4 transports quietly carrying cargo to remote garrisons. History often remembers the spectacular successes and battlefield triumphs. Yet the Shinsen reminds us that technological mastery is more than replication. Innovation requires understanding, adaptation, and the labor of trial and error. Machines are not just assemblies of metal and engines. They are the crystallization of human problem-solving, foresight, and discipline. Without that context, even the most impressive artifact can become a cautionary relic. The G5N also embodies the human dimension of war. Engineers, pilots, and technicians on both sides devoted years to these machines, their expertise shaping the course of aviation history. Some saw glory, like Carl Cover flying the DC-4E with Orville right aboard. Others faced frustration, like Japanese pilots struggling to coax power from failing engines. In both cases, the aircraft became a stage where human ambition met the unforgiving laws of physics and engineering. Ultimately, the Shinsen teaches a timeless lesson. Progress cannot be bought, stolen, or superficially copied. It must be earned through experimentation, comprehension, and iteration. In the silent echoes of the Pacific, amid photographs, blueprints, and fading memories, the DC-4E and G5N stand as enduring monuments, one to success, the other to ambition misapplied. Both shaped the skies of their era and the lessons for those who would follow.